Fluorine is one of the most reactive and intriguing elements on the periodic table. With the atomic number 9 and the symbol F, fluorine is a pale yellow gas at room temperature and belongs to the halogen group, which includes chlorine, bromine, iodine, and astatine. It's the lightest of the halogens and sits in group 17 of the periodic table. Fluorine's chemistry is remarkable for its reactivity, its wide-ranging applications in both industry and medicine, and its influence on the development of modern materials and chemistry as a whole. At the atomic level, fluorine has 9 protons and usually 9 electrons, with a highly electronegative nature, meaning it strongly attracts electrons from other atoms. In fact, fluorine is the most electronegative element, with a Pauling scale value of 3.98, the highest of all elements. This extreme electronegativity is what makes fluorine so chemically aggressive. It readily forms bonds with most other elements, often resulting in very stable, and in some cases, extremely inert compounds like fluorocarbons or Teflon. Fluorine exists naturally as the diatomic molecule F2, which is highly toxic and corrosive. It was notoriously difficult to isolate due to its reactivity, and chemists who tried to isolate it in the 19th century often suffered severe injuries or even death. The successful isolation of fluorine came in 1886 by French chemist Henri Moissan, who developed a method using electrolysis of potassium bifluoride in anhydrous hydrogen fluoride. For this achievement, Moissan was awarded the Nobel Prize in Chemistry in 1906. His method laid the foundation for fluorine chemistry and for the development of modern chemical industries involving this reactive element. One of fluorine's defining characteristics is its ability to form incredibly strong bonds, especially with carbon. This property has led to the development of fluoropolymers, such as polytetrafluoroethylene, PTFE, better known by its trade name, Teflon. Teflon is widely used as a non-stick coating on cookware, but also plays critical roles in aerospace, electronics, and chemical processing industries due to its resistance to heat, corrosion, and chemical attack. Fluorine is also critical in the production of uranium hexafluoride, UF6, which is used in the gas diffusion and gas centrifuge processes to enrich uranium for nuclear power and nuclear weapons. This use underscores how central fluorine is not just in consumer products, but also in highly strategic technologies. In addition to industrial applications, fluorine is vital in the pharmaceutical world. Fluorine atoms are often introduced into drug molecules to enhance their metabolic stability, bioavailability, and binding affinity. Roughly 20 to 25% of all pharmaceuticals contain at least one fluorine atom. A well-known example is the antidepressant fluoxetine, commonly sold under the brand name Prozac. The inclusion of fluorine in such molecules can dramatically alter the way they interact with biological systems, often making them more effective or longer-lasting. Another everyday use of fluorine is in the form of fluoride ions in dental care. Sodium fluoride is added to toothpaste and in many places drinking water because it helps to prevent tooth decay by strengthening tooth enamel and making it more resistant to acid attack from bacteria. This public health initiative, known as water fluoridation, began in the mid-20th century and has significantly reduced dental caries in many populations, although it remains a topic of controversy in some regions. Despite its many beneficial uses, fluorine and some of its compounds pose serious risks. Elemental fluorine gas is extremely dangerous to handle, reacting violently with organic material and many metals. Exposure can cause severe chemical burns and respiratory damage. Some fluorinated organic compounds, such as perfluorooctanoic acid, PFOA, used historically in the manufacture of Teflon and other products, have raised environmental and health concerns. These substances are part of a broader category known as PFAS, per- and polyfluoroalkyl substances, which are often referred to as forever chemicals due to their persistence in the environment and in living organisms. Studies have linked PFAS exposure to various health issues, including liver damage, developmental problems, and potential carcinogenic effects. From a geological perspective, fluorine is not found in its elemental form in nature because of its reactivity, but it is relatively abundant in the Earth's crust, ranking around the 13th most common element. It is primarily found in minerals such as fluorite, CaF2, cryolite, Na3LF6, and fluorapatite, Sa5PO4-3F, which are used as sources for fluorine compounds. Fluorite, in particular, is an important industrial mineral used in the production of hydrofluoric acid, HF, which serves as the starting point for most fluorine-based chemical processes. Hydrofluoric acid, while not technically pure fluorine, is a highly dangerous and important chemical. It can dissolve glass by reacting with silicon dioxide, making it useful for etching glass and cleaning metals. However, HF is also highly toxic and can penetrate tissue deeply, causing serious internal damage without immediate pain, which makes accidental exposure particularly insidious. Fluorine's unique chemistry is also reflected in its role in organic synthesis. Fluorinating agents such as Select Fluor or DAST are widely used in organic chemistry to introduce fluorine atoms into molecules in a controlled manner. This is especially relevant in the development of agrochemicals and advanced materials, where fluorine's presence can significantly influence chemical properties such as solubility, thermal stability, and reactivity. Even in astronomy and planetary science, fluorine has a role. It's thought to be formed in stars, particularly during the asymptotic giant branch phase of stellar evolution, and also possibly in supernovae. The exact origin of fluorine in the universe is still under investigation, as it is not as abundantly produced as many other elements. In terms of isotopes, fluorine has only one stable isotope, fluorine-19. This simplicity aids in spectroscopic techniques, especially nuclear magnetic resonance, NMR spectroscopy, where fluorine-19 NMR is a powerful tool for studying fluorinated compounds in chemistry and material science. In sum, fluorine is a small element with enormous influence. Its unmatched reactivity, extreme electronegativity, and the strength of its chemical bonds have made it both a powerful industrial tool and a subject of deep scientific interest. From the development of advanced materials and powerful pharmaceuticals to its controversial environmental impact, fluorine continues to be a crucial and fascinating element in the modern world.